Go through the last chapter of this computer architecture synthesis lecture. Um, issue and execute are skipped because issue just really talks about very pipeline specific stuff. Um, like like how does data bypass into from allocation to issue, and how do they interact with each other, like producer consumer. If you have two ALUs executing at the same time and the scheduler knows your latency, then they can, let's say your consumer can go, let's say, one cycle after producer, and when it executes it could just read it from the bypass network. That stuff is somewhat intuitive. I don't know that it requires 20 pages of explanation. So that's kind of the issue with the issue stage. And I guess they also talk about like load to store forwarding and stuff like that. So loads can execute out of order, but then of course there's store to load dependencies where you need to look stuff up. And it talks about address generation, and then here they talk about I guess how does load to store forwarding work, where rows or columns, I forget, represent stores, and then loads are represented in the other dimension. So it's kind of like pairwise comparison of which load depends on which stores. And then if, let's say, a store is committed, then the entire column of stores is marked as complete. So then like all the loads in this column can access this store, but not stores that are not completed yet. I guess it's the reverse. Yeah. So stores do it for an entire column, and then loads represent each row. So if you have a load and you're you have a load that depends on like some amount of stores, and those stores are all done or committed, then you can go ahead and execute that load, even if your load isn't perhaps the oldest load, right? And that allows you to load in any order. Right. And then the execute stage just kind of just talks about various execution units, division, how agen is done, how the branch predict unit is built, what are SIMD instructions, which are all these different lanes of instructions, and bypassing results, which I guess they already talked about in the last chapter, and pipelining all these writebacks across different pipelines, and so on and so forth, right? So then you finish your execution, and then you need to commit the actual data to register file, or the architectural map or architectural state. So to review, there's two types of data, right? Speculative data, which is data that isn't updated as the official final state of the computer, and committed data, which is basically, this is kind of a permanent ledger thing, and it's committed, and until you overwrite it, this is the data that'll be in this particular memory location forevermore. Okay. So right. Let's see if there's any diagrams. That's just the introduction. So if you recall, in the allocation chapter, there is the two ways of storing your values. One split between a reorder buffer and an architectural register file, where the latter, this one, is your committed values and your reorder buffer of your speculative values, or you can have a unified register file that's based on a free list as far as resources available, and a map table to map the logical registers to your physical registers. So let's see, architectural state management. So yeah, what's this say? Meantime, you resign the store buffer. Okay, here it's just basically saying that in the reorder buffer, all the values are speculative. And then so when you're committed, you're just going to copy and paste the value over to the retired register file, which is the architectural register in the previous picture I just showed. And then so now if you have a bunch of instructions going and you move this value to your architectural or the committed sort of dedicated set of registers, you're going to need to notify consumers to say, hey, if I'm allocating, if I'm allocating here, I'm still reading from the reorder buffer, but if I'm allocating here and the values kind of move to the RF, the allocation now needs to know that it must go ahead and read from the RF instead of the ROB. And I think in the previous image, this notification is really just the entry in the table that's a 1 or a 0. So you kind of have a map table to say, well, do I look at it in the RF or do I look in the ROB? If I look in the ROB, what entry is it, right? So that's just kind of reiterating at that point. And then here it talks about why a unified register file is perhaps better. So values don't really change location when they commit, so you don't have to re-notify anyone, especially if it's like a bypass network. Like you're in the middle of execution and you need to grab data from within there, you can just grab it from the unified register file as opposed to deciding whether or not you have to pick it up from the RF or the ROB. It's more space efficient because not all instructions in the reorder buffer needs to actually have a value. That's another advantage. And the last advantage they talk about is maintainability, which is just basically saying the reorder buffer is a very centralized structure because obviously it talks a lot of stuff like the end of the pipelines. It talks to any store queues. It talks to any exception or rewind logic or branch recovery logic. And so it's a very, very essential piece of control logic, and we don't really want to add more logic to that if we don't want to. A unified register file is more suitable for these scenarios where separate register files could be implemented on every execution cluster. Oh, that's not the sense I'm looking for. Implementing. Yeah, so ALUs and stuff, they're somewhat decentralized hardware because it's kind of like they're their own modules and they just execute and they grab the instructions when they need them. So theoretically, the reorder buffer and the execution pipeline, all that hardware is somewhat orthogonal. Like the execution pipeline doesn't really care where it gets its information from as long as the information is correct, and the reorder buffer really doesn't care about anything other than being able to keep track of instructions in order, so then everything completes in program order and is coherent. So combining these two sort of orthogonal concepts and then shoving values in the reorder buffers works nicely with these decentralized pieces of hardware. Is just very, very hard to maintain. But having like a unified, register file that's dedicated to communicating with these decentralized piece of, hardware, namely the each tiny module or node in the execution pipeline, that makes a lot more sense as opposed to complicating an already complicated structure. Yeah, so first advantage is you don't have to move data around, it's all in the same hardware. The buffer observes decay. Oh yeah, I guess so they talk about the downside of during the commit stage of this ROB plus RRF versus the register file. So resource reclamation is harder for unified register file. So if you have reorder entry, reorder buffer plus RRF, reclaim is quite trivial because when you commit it, you just move the data into your RRF. Because the data can either be speculative or not. Now, if you have unified register file, then it's kind of alluded to in the allocation chapter, where basically you can reclaim something and shove it back to the free list. You have a physical register allocated by instruction A, when another instruction B younger than A, that writes the same logical register as a commit. So just go back to the allocation, more particular the renaming thing, where I explain exactly how that works and why you must wait for instruction B younger than A to actually commit, as opposed to just fetched and then everything younger than it commits. All right. And then, so the rest of the chapter talks about how you recover when you have a branch prediction or exception. So if you have a branch misprediction, they break down the recovery as two types of recovery that needs to take place in a computer. The first is front-end recovery, which basically is everything you need to do to clean up the front end of the pipeline, which is so that you could start fetching new instructions again. The back-end recovery, which requires like rewinding your reorder buffer or like recovering snapshots of architectural state, is going to take quite a bit more cycles, and you're going to recover all the way so that your allocation stage has coherent physical, logical to physical register mappings again. So then all your data is basically recovered to your point of mispredict or your exception state. So backend takes a lot longer due to this sort of rewind mechanism and a lot of like following breadcrumbs mechanism. The front end recovery is much quicker because you just flush everything. You do them separately, and the reason behind that is because then you can hide some of this back end recovery latency by finishing the first front end recovery and then start fetching instructions. So when you start fetching instructions, you already can have a brand new set of instructions loaded up in your pipeline before your backend is completely recovered. So if you're still recovering your backend by the time your pipeline in the front end is completely filled up with like the new correct instructions, then you could just back pressure the rest of the pipeline and not fetch any new instructions. On the other hand, if your pipeline is filled on the front end with new instructions and then your backend has already completed recovery, then your backend recovery latency is kind of completely hidden, and your effective penalty is just your front end recovery, right? Because then you're not actually bottlenecking or waiting any longer for your backend recovery if all your new stuff is ready to go by the time it reaches allocation stage. So this talks about that, what we just talked about, handling branch mispredictions on this ROB plus RF. So if you have ROB plus RRF, all you need to do is just wait for the all instructions right before the mispredict happens to commit, and then your architectural state, namely your RF, is going to be precisely correct. Then your naming tables at allocation stages are stored by making all entries to point the values in the RF in order to begin the renaming instruction. Yeah, so basically it's kind of free because when you commit the last good instruction, then your architectural register is completely correct, and then you just say, well, all my registers are just going to come from the RF and nothing is going to come from the reorder buffer. So if you need anything else, just go ahead and fetch it from memory if it's not already in the RF. So yeah, you need to wait for the final good instruction to commit. Yeah, so for unified register file, we're talking more of like a rewinding mechanism where throughout, when your renaming table is remodified or modified and renaming happens, you're going to keep a log of what happens. So when you have a branch misprediction, then you have this log traversed, I guess, in reverse order to get back the correct state by the time, yeah, the branch was mispredicted. Yeah, so the breadcrumbs are the logical register the instruction overwrites, namely like, let's say like R1, let's say, and either the physical register identifier, so let's say like P1 assigned to this instruction, or the physical register identifier assigned to the previous writer of the same logical register. So namely for this, if you have two instructions writing to, let's say, R1, and then there's like P1 and P3 that corresponds to it, you need to know what the previous writer is. Because again, you can only free something back to the free list if something new to that same logical register has committed. So these breadcrumbs kind of allow you to rewind and sort of un-overwrite and then unrename your stuff one by one, is what these breadcrumbs do. Yeah, so I mean, you could see how basically a logical to physical register mapping will allow you to, that piece of information allows you to say, well, this physical register is freed and therefore this logical register is freed. But if you have like previous writers to the same logical register, then it's not quite free yet, and then you kind of need to traverse all the way back. Yeah, so traversing this long may take a very long time because that time is going to be, I guess, somewhat linear to how many instructions you have from your branch misprediction. Well, if you have snapshots, so that's what it talks about here. So processors have a checkpoint mechanism that reduces the distance that you need to rewind. So these processors take a snapshot of all the, I guess, the renaming table, so like physical, logical to physical register mapping, and where do you overwrite them. So then you don't have to, traverse back to the beginning of time. So the traversal begins an instruction where oh, I see, cool. Okay. So actually they just take a periodic snapshot of where all your registers are committed or otherwise, well, the mapping, so you know where to rewind. And then so let's say you have a branch which predict at instruction 10 and you discover it in instruction 20. Normally you need to rewind all the way back from 20 to 10, but if you take a snapshot at 15, your traversal can actually begin on instruction 15 and then you have your distance in that way. Yeah, so for example, in this processor, it would just take the first checkpoint that's younger than your branch and then rewind it to the branch, given a branch mispredict, right? And then the worst case scenario is like there's no checkpoint that's actually younger than the mispredicted branch, in which case you basically have to do the farthest distance where you go from your youngest instruction and rewind it all the way to your mispredicted branch. So that's the farthest. Okay, so some processors also have like a list of basically free list as part of the checkpoint. So when you start rewinding at like, let's say instruction 15 back to instruction 10, where instruction 15 is your snapshot, you also know exactly what was available in your free list then, so then it makes the rewinding a little bit easier. And then, so that's recovery from branch mispredict. Yeah, the only thing that's different with exception handling is you. So branch mispredicts for unified register file, you don't have to wait for the branch mispredict to complete, and you can start rewinding it prior to save time. But recoveries from exception, you must wait for the exception to commit, and the reason is because you have to know that the things that so you have to know, like, you have to be sure that the thing that caused the exception isn't speculative. So if it was in a mispredicted branch, then you actually don't need to do the hard work of recovery and doing all the exception handling. You can just kind of rewind your way through it. But then, I mean, obviously, then that presumes that you're recovering to a mispredicted branch. Yeah, another point is, given if you're rewinding before committing your mispredicted branch, if your mispredicted branch was on the wrong path, so your mispredicted branch is already in another mispredicted branch, then you have to rewind it anyway. So it's okay to not wait for your mispredicted branch to commit before rewinding. And if it's in the right path, then you're mispredicted it anyway, so then you have to rewind, right? So, yeah. But for exceptions, you have to wait until commit time. Because exceptions can kind of crash the machine and stuff like that. The second reason we need to provide, so we would be as if all instructions. So this is very similar then to the ROB plus RF recovery, where you have to wait for the thing to commit, and then you just flush everything, and then whatever remains is the actual good piece of data that's on non-speculative, is what this says here. Because if you start rewinding and start recovering without this being committed, then well, yeah, I guess it's just extra work. At this point, the speculative state is recovered using one of the mechanisms previous section. Okay. Front end is redirected to start. Yeah. So you commit your exception, the thing that's causing the exception, and then you flush everything on the back end, recovered using like the rewind or the ROB plus RF situation to get rid of all the speculative stuff. And then once you do that, then everything looks like it's executing in program order, which is fine. And then the front end will start recovering again and start fetching new instructions. What I want to say, so new instructions. So then basically TLDR, right? Like the ROB plus RF recovery, or this sort of rewind recovery based on breadcrumbs in the renaming table. They're both sort of backend recovery. The backend recovery for reunified register is a lot slower, which is why we have this backend front-end graph earlier in the chapter somewhere. Yeah, so backend recovery is all these sort of rewinding, and your front-end recovery can actually fetch new instructions from the exception handler. And I guess you could do this even before the backend recovery has completed. Anyway, so that covers sort of commit and retirement of instructions, and therefore we've covered everything from the beginning where we fetch instructions from memory, and then how to rename and allocate all resources. We sort of skipped how it's going to be decoded in x86 because that's more semantics, and we sort of skipped over the issue and execute stage. But rest assured, once you allocate it, then you just outsource the work to the ALUs to execute it. Once everything's executed, then we commit it to a register file, which then can be either architectural or not architectural, or we could commit it to a reorder buffer field, which it will be speculative until it's committed, and then it'll be copied over to a retired register file. And then given that, there's a couple types of mechanisms where you can recover. If it's the ROB plus RF, you simply need to flush your ROB on the back end. If it's a unified register file, then you actually need to do the more complicated process of rewinding a lot of stuff, because you did a lot of renaming, and then the renaming depends on like the previous older instruction or younger instruction on overwriting that same logical register file with a different physical register file, so you can kind of recover it based on those rules. Yeah, and then recovery for an exception is basically the same as recovery for a branch mispredict, except you usually handle them at commit time, whereas branch mispredictions, you can handle it at pre-commit time without doing extra work. That kind of concludes sort of like a computer architectural whirlwind study. So hopefully this is a good refresher.